So good afternoon. I'm Amit Ashok. I'm with the College of Optical Sciences at University of Arizona in US. And I just want to start by thanking the organizers, especially Yanis and Bulat, who invited me. And I sort of decided to come to present here at the last minute. So I'm glad it all worked out, including the computer setup, because otherwise I would have to do it virtual, and I might be as well in the US. So I'll be talking about quantum-inspired optical super resolution imaging, which would be an application of quantum, let's say, imaging in optical domain, specifically for super resolution, which I'll talk about. And I want to acknowledge support from DARPA across 3 programs. So we have been supported in this work from 2017 till now. And I also want to acknowledge my collaborators, Professor Saikat Gua, who is one of my colleagues at University of Arizona, Dr. Zachary Dutton, who is a collaborator at Raytheon BBN, and then my former postdoc, Ronan, Dr. Christos Gagotos, he's a research faculty at Arizona, and my student Quan, and Saikat's student, Michael Grace. So it's a teamwork, and I'm representing some of the work we did it all together on the DARPA program. All right, so let me begin with some motivation, because the imaging and the optical super resolution, I would imagine, would be new to many of the folks in this community. So let's see. All right, so I wanted to show this astronomy image because, or image of this galaxy, because one of the applications of what I'm going to talk about could be in astronomy, but it can also scale to very small scales in microscopy. So if you look at sort of this image, which is taken by Hubble telescope, we can see, plenty of stars, but at some point you stop seeing the detail, right? You can't resolve. And if you take, if you take your ground-based telescope, you can do the same thing with space-based telescope. If you want to see more detail, you have to make the mirror bigger and bigger and bigger. But there's some point where the cost of making the mirror bigger is astronomical, no pun intended. So there's only so much you can do by making the mirror bigger or even doing interferometric combination. One of the questions is that for a given mirror size of a telescope, or for example, microscope, what is the most detail you can resolve, right? What are the smallest features you can resolve? So the question is, what is the fundamental limit for doing that? And at least, okay, so let me play this. And actually, this would be example of using bigger and bigger telescope. You can see deeper and deeper, more and more resolution. And this is pretty amazing that how deep you can go. But these are using ground and space-based telescopes, combining many, many such telescopes together. So you can see you can keep zooming on, but at some point, the cost of doing that becomes billions, tens of billions of dollars. So you can't do that anymore. And even physically, it's hard. So again, the point is that even if you had the biggest telescope, it has a limit. What is that limit, and is that fundamental? Okay, so I think I'll stop here. So in optical imaging, that limit is known as, from a historical point, known as what is called the Rayleigh limit. So what the problem I'm talking about, imagine you have 2 stars. They're centered about the optical axis of a telescope. You have the lens, which is basically a telescope mirror, the simplified version. You have some size of the telescope, D, the aperture size. And let's say we are just looking at a single wavelength, just to make it simple. And the starlight can be considered to be spatially incoherent light. So it's a thermal source, right? It's completely describable from semi-classical optics. There's nothing quantum about it, so to speak. So what the telescope does, it focuses the light and it forms an image of a star, which I'm showing by the Gaussian function. If you have 2 stars, you have 2 images, right? You can see that. But as the stars get closer, which is equivalent to zooming into the sky, then these images start overlapping more and more. And what is shown in the purple curve is the superposition of those 2 intensity images. So at some point, you can imagine if the stars get too close, at least with our eyes, they will appear to be one star, like one image blur. Okay, so from a visual perspective, that is the limit of resolving the star, and that is proportional, that theta is proportional to lambda or d. Lambda is the wavelength, and d is the aperture. So you can see why making the telescope mirror bigger helps, because you can resolve smaller and smaller detail. So the question is that limit fundamental in a sense of a rigorous sense of information theory? And actually, when the original limit was proposed was by Lord Rayleigh in 1879, so this is way back, it was supposed to be a visual resolving limit, where the observer was human eye. Now it has been replaced by computer algorithms. So for a computer algorithm, if you just see one bump, but there are 2 point sources, you can still probably resolve it, right? So the rigorous way of answering that question is to actually do a rigorous calculation, and we can do that with classical optics, but we can also use quantum optics to try to answer that question. So this is where the quantum-inspired imaging comes into place, because everything about the system is completely classical. There's no quantum source, there's no quantum receiver, okay? So you can describe the state of light using the density operator rho of theta, and I won't get into the details of it. For a weak thermal source, you can write it like that, and using that quantum state of light, you can then calculate what is the quantum Fisher information, which is the absolute limit of how well you can resolve the 2 stars, okay? And then you can actually compare that to what a traditional telescope achieves, which is what it is doing by taking the optical light and forming an image and photo detecting it in the focal plane array. So the question is that the best measurement you can make, or does it actually reach the quantum limit? So this is a classical Fisher information calculation. Given the imaging measurement of a traditional telescope, you can apply classical Fisher information and find what is the precision with which you can estimate theta, which is the separation of the 2 point sources. So in this plot, the vertical axis is information. More informations mean better resolution. Horizontal axis is the separation of the star. And what you see in the vertical line is the Rayleigh limit. This is the traditional limit, or at least the visual limit that people thought that you can't go below. So if you do the classical Fisher information on the image measurement, you get the curve in the dashed line. And you can see that if you go below that limit, it's not like all information is lost, but as you get closer and closer, you lose the sensitivity. And ultimately at 0 separation, where the stars are basically undiscernible, you get 0 information. What is interesting is if you compute the quantum limit, given the quantum state description of light, semi-classical light, what you find out is that the quantum Fisher information is actually constant all the way down to 0. So we can ignore at the 0 value because that's a pathological case, but it shows there is a huge gap between the currently world's best telescopes, what they're doing, and what they can be doing. Okay, so this was a groundbreaking result by Manke-san, who published this in 2016. And since this field has exploded, trying to take that result to the next level. So the question is, what kind of optical measurement will actually saturate or meet that quantum limit? And it turns out that in Manke-san's original paper, he also proposed what kind of measurement would achieve that. And in fact, the top one is the traditional measurement, where you take the image, you photo-induce that into a current in a focal plane array. The bottom is what he proposed. And basically, the idea was optical preprocessing. If you take the optical field and sort it into spatial modes, in this case, sync Bessel modes for a hard aperture, and measure the light and photodetectors behind these modes, then you can actually achieve the quantum limit. And it will do much better, especially in this deep sub-Rayleigh region, which is below the traditional limit. Okay, so that was sort of a surprising result. So here, what I'm saying is that the benefit of this mode sorting measurement comes in this regime. This is known as the sub-Rayleigh regime, also known as the optical super resolution regime, because you're super resolving beyond what is thought to be a physical limit. It's not. So you can see the deeper you go, the more benefit you get. Okay, so that was kind of a surprising result. But this result was of limited utility, and the question is why? Well, I mean, there are very few problems in this world where you have 2 point sources with equal brightness, incoherent, and it's a toy problem, right? So if you want to generalize it to real world problem, we want to look at, as an example here, looking at multiple stars or point sources, right, in a field of view as shown here in the bottom, okay, and where the number of stars are not known, that's more realistic problem, and the brightness of stars are not known. In the previous problem, we knew there are 2 stars centered on the optical axis with equal brightness, so it's like a perfect textbook problem. But in real world, we don't know that. So imagine if we have p stars in the field of view, showing in that circle. Each one has x and y location, okay, and brightness bi. So if they're p stars, there are 3 p parameters that you want to estimate from a imaging measurement and then precisely localize. +1 is because you don't know how the number of stars, so you also have to estimate how many stars there are, and then find their positions, okay? So it turns out that if you try to take the framework from Manqueson's paper, which is calculate the quantum Fisher information, but now for more than one parameter, you can actually do that, but there is not a necessarily, there doesn't exist a measurement which necessarily achieves that optical limit or the quantum limit. And that, I won't get into the detail of that. Essentially, it has to do with the parameters that you're estimating, they have to commute. If they don't commute, you can't simultaneously maximize the information for all of them. So the question is then how do you go about solving this problem? Because we know how to solve a single parameter problem, but we have a multiple parameter problem. So in a way, what you can do is cheat a little bit and do this kind of a measurement protocol. So this is a lot of detail. I'll try to describe the very high level. So imagine you have access to n copies of this quantum state, rho of theta. Now theta is a multidimensional parameter. One way you can do this measurement, which is the traditional measurement up top, direct imaging, is you can just take all of those measurements, and if you apply the POVM operator, which will realize the measurement, and that would be the imaging operator, that would give you the traditional image, right? Which we know how it performs because of that curve, okay? So that's the baseline that we have. Now, there are two other ways where we can estimate this multiple parameters, essentially by making the problem easier. And it has to do with, instead of estimating all the parameters simultaneously, we are going to estimate one parameter at a time, okay? So convert a multiple parameter problem into one parameter problem. And I'll talk about that in a moment. But let's imagine we are just doing one parameter. What we do is we divide the total resource, which is n copies of the photons, or the exposure time, into smaller pieces, and do this sequentially. So we make one measurement, update our information of what we learn about this star constellation, and then feed that back into the quantum state description, as in revise that, and then do that again. And we keep doing that till we run out of resources, which is number of photons, or we achieve a particular fidelity. So again, I won't get into the details of this, but you can think of this kind of operation as what they call a LOCC operation, which is local optical, which means that's where you're doing the optical preprocessing. And then the feedback that you have for the next measurement is not an optical feedback, is a computational, classical computational feedback, CC. So you take a measurement, infer the state of the constellation, and then feed that back into the new optical measurement. So the middle one is doing that with a Fisherian setup where you're using quantum Fisher information. But let's say you have prior information about the star cluster, you can do the equivalent of that measurement protocol in the Bayesian sense. Okay, so that falls in the prior. And even if you don't have a prior, what we can do is the first set of measurements, which I've shown in yellow, is a traditional imaging measurement. So you just point your telescope at that, take a picture of that. From that, you try to estimate these stars. Of course, you're not going to do a good job, but you'll initialize the prior. Okay, so now you have a prior, although it's a bad one, and then you can feed that back into the measurement design. So you keep doing that on the bottom one, and I won't get into the details. That is known as a personic projection measurement. The middle one is known as the SLD, symmetric logarithmic derivative measurement, and the top one is traditional one, okay? And there are a lot of details I won't get into because of time. There is a whole backend algorithm in terms of the inference, which is going on for the classical computation feedback, the CC part, which I won't have the luxury to get into. And we are going to actually upload this into archive. So for those of you who are interested in the details, I'll be happy to share that. So let me show you what happens, if we implement this protocol. And again, I will remind you, there is nothing quantum about the source or about the measurement. All we're using is the quantum theory of light to apply it to semi-classical light to find what are the limits and then try to achieve that. In this case, we are not necessarily achieving the quantum limit because one, it's hard to calculate, and second, it's even harder to achieve, but we are trying to be inspired by that and do something in that spirit. So here's an example of 4 stars in a constellation, and the radius of this circle is actually below the Rayleigh limit. So if you were to just look at these 4 stars in a traditional telescope, you'll just see one blob. You cannot resolve that there are 4 stars, okay? So the black points are the ground truth because this is simulation. The blue points are if you take that starlight on the focal plane array, with the eye you can't resolve it, but if you put that in a computer algorithm and do some smart processing, then you can actually get some estimate of where they are. Those are the points in blue. You can see they're not close to the original points. And the one in red is this Bayesian adaptive sequential estimation that we are doing using personic measurement, which leverages the quantum description of light and then makes the optimal measurement, at least for a single parameter case. Okay, and this is the final estimate. So let me show you also, because this is adaptive, you can actually see the evolution of that estimation as the measurement is going on, feeding back how the estimate is being refined. So hopefully this works. So on the very left is the personic measurement, which is a fully Bayesian in the optical preprocessing, and on the classical feedback, the computational feedback. The middle one is the SLD measurement, which uses quantum Fisher information. So it uses a Bayesian feedback, but on the front end, it's using Fisher information instead of Bayesian information. So it's not fully able to leverage the updates of the priors. It's using point estimates instead of priors. And then the last one, which is fixed because we can take all of those measurements at the same time and then process, is the classical imaging measurement, right? Where you just stick a focal plane array. And this is like a perfect focal plane array that you can have access to. So you can see over time in this, the estimates are dancing around. In the personic case, which is the leftmost, it gets pretty close. It's not perfect because this is done for finite number of photons. Asymptotically, we are also exploring if we can show that it will actually converge to the true ground state. But you can see the Fisher-based measurement is not doing as well. So it helps to inject the prior into the sequential hypothesis or sequential estimation loop, which includes both optical preprocessing and the backend feedback. Okay. So we are very excited about this because we can also do this for, in this case, actually the brightness of the stars were uniform, but even if it's not uniform, the protocol will estimate the brightness, and it can also estimate the number of point sources. It may not necessarily get it right. If there are, let's say, 5 point sources, it may estimate it to be 4 or 6, but then, so there's an error in that, but then it will try to localize to the best possible precision. So one thing actually in this kind of task is, how do you even measure how well your imaging protocol is doing? Because there is not a single objective function, right, which will take all the localization error that you're trying to minimize, take the brightness and the number of point sources. So even trying to measure the performance of such a system is quite mathematically challenging, because different measures focus on different fidelities of the cluster estimation. Okay. How much time do I have? 2 minutes, perfect. So I'll end with this statistical result. So I just showed that to you for one constellation. We of course repeated this for multiple constellations. This is not a, closed form theoretical result. So this has to rely on numerical simulations. So we took 10 constellations. These are all sub-Rayleigh. So in a traditional telescope, they just look like a blob. We ran 100 Monte Carlo simulations because of the photon arrival process is stochastic. And in this case, we used a total exposure budget of 500,000 photons. Okay, and we adapted every 10,000 photons. So that's 50 adaptation steps that we took till we ran out of photons. And the error charts on the right is showing the localization error. So for every termination of that loop, we computed the true position, or we know the true position, we computed the estimated position, and we plot that as a histogram. The horizontal axis is in terms of the Rayleigh units. So smaller is better in terms of the error. And the orange chart is the histogram of our method. The blue chart is the traditional, the best telescopes which exist right now. So you can see there's about a 4-fold or 5-fold improvement in the localization precision. And that's when we know the number of stars is fixed at 4. And the bottom one, if we don't know the number of stars, we have to also estimate that. There is some penalty in terms of estimating that. But even in that case, the performance is not reduced by too much. So of course, we are looking at generalizing this to higher number of stars, and then more importantly, generalizing this to scenes which are distributed. They're continuously varying, because stars, you can model as point sources. But if you're trying to do the same thing, looking out in the world, tracking things and localizing features in the real world, these are continuous objects. And you can imagine the number of parameters it would take to generalize to that. So that's the sort of next step we are working on. I think with that, I've run out of photons. So we'll stop here. Thank you.
Thank you for the fascinating talk. Okay, so I'll begin with the organizer's question. What do you think will be the main use and challenge of entanglement-assisted communication networks?
So that's a hard one because I don't work, one, in networking, even classical, and second, in quantum networking. But nonetheless, I think one example I can think of where that would benefit from quantum entanglement over distances is, imagine you have an array of these telescopes. So this is a very well interferometric application in astronomy, started in radio astronomy, now they're doing it in optical. You have to bring the light from these different telescopes and combine them coherently. That's actually what LIGO does in a way. So that's a very good example of a very, very sensitive interferometer. So if you imagine you have these very large telescopes, let's say one in Chile, which is, I think they're building a 30-meter telescope or 35-meter. And then they have another one in, I think, in Hawaii, which is also going to be of 30-meter. If you can combine those two telescopes, that will give you an equivalent of 60-meter telescope. But combining that over, I don't know, the distance is thousands of kilometers, right? So if you could do this quantum entanglement of the classical light that these two telescopes are collecting, you could process that. Otherwise, there's really no way to process that light from two such distance telescopes. So that could be potentially a use case of distributed sensing.
Challenge?
Challenge, let's see. So I guess, thinking of the point-to-point versus the multipartite, if you want to combine this into 3 or 4, telescopes, let's say one in Australia, they have a big one there, then you have to be able to extend that. What else can I think of? I don't really know enough to comment intelligently on that.
Do you have any comment for 6G? Or
6G, yeah. So actually, I was thinking about that, because I've heard this many times now. So I'm thinking at some point, and we are already witnessing that in astronomy, for example. Again, I'm going to take that example because that's close to my heart. You have a lot of backyard astronomers, like amateur astronomers, right? And they actually have access to pretty decent sized telescopes. So if you can somehow combine the light from those telescopes, and that could be running over through 6G or a quantum network, it could be part of 6G. I mean, it's not a mass market application, but it could enable this mass scale distributed sensing. And you could network thousands of telescopes in principle. I don't know how the logistics of that is going to work out, but that could be one use case of 6G, especially if it has quantum capabilities.
I wonder if you assume that the number is, you don't know the number, you assume that it's smaller than what it really is. Would it?
So in this application?
Yeah, would it recognize some of them?
Yeah, so what will happen is that if you underestimate the number of stars, which you could possibly do, then the algorithm will be forced to combine some of them because it cannot go above, we put an upper bound on the number of stars. Okay, and you have to put an upper bound, otherwise the complexity explodes, at least in this scheme. So it will basically merge probably the closest stars that it's finding into one. So you won't be able to resolve. So that's one penalty. Yeah. So if you can afford, you always want to overestimate. But again, you don't know what you don't know. So you could definitely make that mistake.
We'll have to leave further question to the panel.
Okay.
So let's thank Amit again.